So, a new paper just dropped from DeepSeek AI. And get this, it challenges a core assumption that pretty much every single major AI model is built on. We're going to dive into this because, look, if their findings hold up, this could literally change how powerful models get built from here on out.
Yeah, I know. It sounds a little crazy, but it's totally true. From GPT-4 to Llama 3, all the big ones, their fundamental architecture relies on a principle that's been the unquestioned standard for over a decade. I mean, it just worked, right? It scaled up, and so everyone kind of just assumed, yep, that's the only way to do it. But, and this is the key, it turns out that whole solution was hiding a big secret trade-off.
So what is this decade-old idea? Well, it's called a residual connection, and a really good way to think about it is like an information highway right inside the AI model. See, before this came along, trying to train these really deep networks was a nightmare. The signals would either just fade away to nothing or they'd explode as they went through all the layers. It was super fragile. Residual connections created this stable shortcut. They basically rescued deep learning and made the massive models we have today even possible. And you know what? They worked so well that people stopped even thinking about them. They went from being a clever design choice to just basic infrastructure.
Okay, so here's the crucial point. That stability, the thing that saved everything, it came with a price tag. The information highway was super stable, for sure, but it was also just a single, narrow lane. For a long time, as we were just making models bigger and stuffing them with more data, that wasn't a huge deal. But now that we're pushing AI to do really complex reasoning, that little narrow path has turned into a massive bottleneck.
So, of course, researchers had a pretty obvious thought. Hey, if one lane is a bottleneck, why don't we just build more lanes? And this is what led them to a really promising, but as it turns out, a really unstable idea. They called this concept hyperconnections, and the idea is actually super simple. Instead of that one single information stream, you have a bunch of them, all running in parallel. What this does is it gives the model a much wider internal highway. It's like giving it more workspace to think, more flexibility to mix and match information in new ways. And yeah, on paper, this looks like the perfect upgrade, right?
And, well, there's the trap. The upsides were so tempting. I mean, more internal capacity, way more potential for powerful reasoning. Who wouldn't want that? But the downsides? Oh man, they were an absolute deal breaker. When you have all these streams just mixing together freely, you have zero control, and that leads to this unpredictable, totally catastrophic instability.
And this right here is what made the whole hyperconnection idea so incredibly risky. You'd be training the model, and for thousands and thousands of steps, everything would look perfect. The metrics are going up, it's learning, everything looks great. And then, poof, without any warning, the entire training run would just collapse.
I mean, just look at this collapse. At step 10,000, everything's green. The model is learning beautifully. But fast forward just 2,000 steps, and it's a total catastrophic failure. The loss just spikes, the gradients explode, which, by the way, is basically the math equivalent of a feedback loop just screaming completely out of control. And the model is toast. It's useless. And that kind of unpredictable failure is just not acceptable. Not when a single one of these training runs can cost millions of dollars.
So this is the exact problem that DeepSeek decided to tackle. They looked at this and realized, you know what? The idea of a wider highway isn't wrong. It just needs some traffic control.
And their solution is called Manifold-Constrained Hyper-Connections. Yeah, I know, it's a mouthful. We'll just call it MHC. But the core idea is actually beautifully simple. MHC keeps that multi-lane superhighway from the hyperconnections idea, but, and this is the magic, it adds a set of really strict mathematical rules that control how the information is allowed to mix between all those lanes.
Okay, so MHC really works on three core principles. First, yeah, it lets all the different streams blend and exchange information. But second, and this is really the genius part, it forces that mixing to preserve the total signal strength. So information can get moved around, redistributed, but the total amount can never be amplified or lost. And third, it uses a specific mathematical structure to literally bake stability right into the architecture itself.
And that's really the core insight here. DeepSeek basically figured out how to get the best of both worlds. You get the rock-solid stability of the old-school single highway, but you combine it with the massive capacity of a brand-new superhighway.
You know, this is what really separates MHS from every other attempt that came before it. Stability isn't something you're just hoping for by tweaking a bunch of settings. No, it's a mathematical certainty. It's a structural property of the network. And that guarantee is what makes this whole approach practical and not just another dangerous experiment. Okay, so a cool idea is one thing, but the big question is, does it actually work in practice? Well, DeepSeek put it to the test on models up to 27 billion parameters. And yeah, the results are pretty striking.
Just take a look at this jump on GSM 8K. That's a big benchmark for math reasoning. The standard model, it scores about 46.7%. But the model with this stable MHC architecture, it jumps all the way to 53.8%. I mean, that is a massive leap in a really critical reasoning skill.
And it's not just math either. These gains are consistent right across the board. On logical reasoning, performance jumps from 43.8 to 51. On general knowledge, a solid improvement from 59 to over 63.4. So we're not talking about minor tweaks here. These are significant, real-world capability gains.
So here's the really important thing to grasp. This isn't just about throwing more data or more compute at the problem. That's how we've typically scaled AI for years. No, this is a fundamental improvement in the model's architecture. It's a smarter way of using the resources it already has, simply by making the internal information flow better.
And get this, here's the real kicker. They managed to get a 400% increase in the model's internal data capacity, but the training time only went up by 6.7%. Let that sink in. That level of efficiency it's almost unheard of. This tells you that this isn't just some cool idea on a whiteboard. It's a practical, scalable, and incredibly powerful engineering solution.
So how'd they pull this off? Well, with some serious engineering shops. We're talking custom GPU code, clever tricks to save memory, and totally optimizing how data moves around during training. This is one of those rare cases where you see deep theoretical insight combined with absolutely top-tier practical execution.
All right, so let's zoom out for a second. What does a breakthrough like this really mean for the future of AI? What are the bigger implications here?
If you look closely, DeepSeek kind of has a pattern. First, they drop a shockingly powerful model out of nowhere, like their R1 reasoning system. Then, a little while later, they publish the foundational research that explains how they did it. So this MHC paper, it feels like a preview, doesn't it? It's like we're getting a sneak peek under the hood at the exact technology that's probably going to power their next generation of flagship models.
Strategically speaking, this is a huge statement. It signals that DeepSeek isn't just playing catch-up. They are innovating at a really fundamental level. And by publishing all this openly, they're showing a ton of confidence. They're basically throwing down the gauntlet and challenging all the other labs to keep up. And what this does is it creates a whole new path for scaling AI that isn't just about who has the biggest pile of GPUs.
And that really leaves us with a pretty fascinating final thought, right? For over a decade, pretty much everyone in the field just assumed that residual connections were a solved problem. It was settled science. And then DeepSeek comes along and proves they weren't. So it really makes you wonder, what other foundational ideas in AI are we all just taking for granted right now, just waiting for the next big breakthrough to come along and shake everything up?